Hello and welcome to the first video in my ordinary differential equations series. So here I'll be explaining some of the methods behind most kinds of ODEs that you'll see. So I'll go into what the method is and I'll go into plenty of practice problems. And so this whole series should cover really any kind of ODE that you would see in your ordinary differential equation class. So if there's something that you're confused about or want more practice with, just look that up in this playlist and I'm sure you'll find it here. So seeing as this is the first video, we should go over some terminology and what an ODE really is. So previously in your algebra classes, even though you've seen equations a lot more complicated than this, you may have seen something like x plus 2 equals 1, just for example. And here you would say that x equals -1, and that's your answer, right? And so here, as you can see, there's one variable in this equation. Of course, there could be more unknowns or whatever, but at the end of the day, your final answer is going to be some form of a number. And so now we're working with a different kind of equation. So here we have, let's say, for example, the derivative of y with respect to x equals y times x. So this is what we would call a first order linear ODE. So I'll write that here. And so it's linear because the actual variable that we're solving for is y. And that's because we have a derivative of y. So that's a sure sign that you're going to be solving for y. But that y, everywhere it appears, which is just here in its actual form, it's linear. There's no square here, there's no cube. So that's when we would call it linear. And it's first order because the derivative is the first derivative. If it was the second or third derivative, for example, it would be it would be second or third order. So this is first order. And so if we had, for example, d cubed y dx cubed equals y cubed x, just a random example, this would be obviously non-linear because y now has a cube, and not only that, but we're taking the third derivative, so this is actually third order. Okay, all right, so this is just kind of some terminology that I'll be throwing out, but for now, you just need to know basically what an ODE is and that they involve derivatives and integrals. And so in order to sort of progress in this class, you'll definitely need some derivative and integral knowledge. So that's why in many universities, the prerequisites are calculus 1 and 2, exactly for those differentiation techniques and those integration techniques. But today we're looking at linear first order ODEs, so this kind right here, and we're going to be looking at a specific kind of them. So the kind that we're looking at today is in the form a of x dy dx plus b of x y equals c of x. So this is first order because we only have the first derivative, and it's linear because y only appears with a power of 1 here. So this is the form, and so what we're actually going to do here is we're going to divide everything by a of x, and keep in mind that a of x, b of x, and c of x are just any equation or polynomial in terms of x. So that's what the of x means. So we're going to divide by a of x, and we're going to say dy dx plus, we'll say p of x y, and p of x is just defined as b of x over a of x, but we call it p of x just for simplicity. And so we call this q of x for the same reason, just to rename something and make it a little bit shorter. So this is sort of your goal, is to have your ODE in this form. So this is step 1, is getting your ODE in this form. Step 2 of this method is going to be to calculate what we call the integrating factor. And so bear with me here. It'll make sense shortly why we do this, but we're going to calculate a quantity that we call mu of x, which equals e to the integral of p of x dx. So trust me, this is very important, and you don't need to understand exactly why we're doing this right now. It'll become clear, I think, shortly. So after you've found the integrating factor, the third step is just going to be multiply the whole ODE by the integrating factor. So that'll turn the ODE into something that looks like this. So remember, this is what the ODE looks like. It's in this form up top. So now mu of x dy dx plus mu of x p of x y equals mu of x and then the q of x. So all we did was multiply both sides by mu of x. All right, and so step 4 is just going to be rewriting the ODE again. So actually, this right here is the result of a product rule. This is the result of d dx, mu of x, and y. And so we can kind of, I guess, convince ourselves of this in a second, and the right side stays the same. We just rewrote the left side. So if we're doing the product rule, then we would do mu of x times y prime, right, plus mu prime of x times y. That's the formula for the product rule. And so I'm trying to convince you that this is exactly what we have written here. And this part is easy. Mu of x y prime just means mu of x dy dx, so they are the same. And the right side is mu of x p of x y, but we have a mu of x prime times y. And so remember how we said mu of x equals e to the integral p of x dx? Well, if you took the derivative of that, then it would just bring the p of x down, basically. And then you would be still left with mu of x, because when you take a derivative of an exponential, of course, the exponential in some form always remains. So mu prime of x would actually equal e integral p of x dx times the derivative of the e to the, I call it sometimes. And so that is just the derivative of an integral, which is p of x. And so, of course, sorry, this is a prime here. And of course, this is itself mu of x, as we have already defined it. So that means that mu prime of x equals p of x times mu of x. And so that's why we have mu of x times p of x. And then the y is there because of the product rule that we discussed earlier. So that's just proving to you that we have not changed the equation at all by rewriting it from step 3 to step 4. And so now, the reason that we rewrote this in the first place is because, well, now we can integrate both sides with respect to x. And so this is going to be very, very helpful, and you'll see why here. So if I were to integrate both sides, then the left side, well, the derivative just disappears, because the integral of a derivative is just the original function. So the integral is just going to be u of x, y equals the integral of mu of x, q of x, dx. And this is because we just integrated both sides with respect to dx. All right. And so that's step 5. And I'm laying these steps out so that you can follow them directly in this way for any problem of this form that you may find. And so then number 6, you have your answer. So y, the goal variable, is just going to be 1 over mu of x times the integral of mu of x times q of x dx. And as you can see, the final answer here does involve an integral. So that's again why I mentioned how we need to have some integration experience before moving into this class. But so this is the actual method. This is what you'll do every time for this kind of ODE. And of course, I've showed you this just in, variable form. I'm not actually working with any numbers here. These could be any polynomial, for example, or any function rather of x, for example. It doesn't need to be a polynomial. So now I'll move into some examples just to sort of show you what this method actually looks like. But of course, we're going to follow our 6 steps every time. So let's start with an example. So these, I'll do a few in total here, but we'll start with, let's say we have t dy dt plus y equals t to the 5th. Now, as you'll notice, the variables are a little different here. Instead of working with y and x, we're working with y and t, but I'm doing this to show you that it works the exact same way. So you don't need to be familiar with any 2 combinations of variables. You'll be able to do this for any variable, basically. So what we notice here is that what we called a of x previously is now a of t, and it's just the polynomial that comes in front of the derivative, and so here that's just t. What we called b of x is just b of t, which is 1, because there's nothing in front of here. What we called c of x, now c of t, is t to the 5th. But remember, we want to divide by a of x, which in this case is a of t, which is t. And I'll start calling them by their actual variable name. So a of t is t, and so on. But let's divide by t. So this leaves us with dy dt plus 1 over t times y equals t to the 4th. All right. So now, remember the next step is finding the integrating factor. We call this mu, this case of t equals e to the integral of p of t, which is the whatever in front of the linear variable. So here it's 1 over t, so e to the 1 over t dt. So this is going to be the integrating factor, so let's actually solve this. Well, this is the same thing as e to the ln of t, because the integral of 1 over t dt is just ln of t. All right, so we know that e to the ln of t just equals t. They kind of cancel each other out. All right, so remember the next step is to multiply the whole ODE right here by t. So let's do that right here. So now we have t dy dt plus y equals t to the 5th. And of course, this is kind of, we just sort of recovered the original equation, and sometimes that happens, but what's important is that now we have the integrating factor, and now we can undo the product rule right here. So next step, rewrite this as a d dt times the integrating factor, which in this case is t, and then multiply that by the variable you're trying to solve for. So right there, and this equals still the right side as is. Write that a little bit better. Ooh, sums up with my 5s. Okay, here we go. And so now the next step is to integrate both sides with respect to t, which is going to leave us with ty equals the integral of t to the 5th dt. So ty then equals, this is a nice integral, this is just t to the 6 over 6. And of course we still can't forget our plus c, so we're going to leave that there. So now we can solve for y. Of course, the whole goal here is to solve for y, and now it's just like any other algebraic equation that we've ever seen before. So we just divide by t. So this will say y equals t to the 6th over t times 1/6, but we can just cancel 1t. So this will be 1/6 t to the 5th plus c times 1 over t. And so this is our final answer for what is y. And so we solved for y, which is a function of t, when we were given this equation right here. So that's the essence of every ODE, is solving for a variable that is sort of hidden behind a derivative. So in this case, y is the goal, right? But it's hidden inside of this derivative here. So in order to solve for it, we need to employ this specific linear first order ODE technique. And so we eventually do get y, and it doesn't end up being that bad. You know, it wasn't too hard to get there. And this is a pretty common theme. A lot of these ordinary differential equations really aren't too difficult. You just sort of need to know the method. And that's why I outlined sort of 6 concrete steps up here that you can follow and get the correct answer without fail, you know, assuming that you are minimizing any mistakes along the way. So let's go over another example. I feel like the best way to learn is by doing examples. That way you make sure that you actually know the question, what the question is asking. So let's say we have a ODE that says e to the x dy dx plus y equals 1. Now remember, we always want the derivative to sort of be alone, and so we always divide the entire equation by whatever is sitting out next to it. So this would give us dy dx plus y over e to the x equals 1 over e to the x, like this. All right, and so then the next step, always finding the integrating factor. So in this case, we're solving for y, so the integrating factor is going to be a function of the other variable. In this case, that's x. So mu of x equals e to the integral to whatever's in front of the variable we're solving for in the ODE. Here it's 1 over e to the x, so 1 over e to the x dx. And so this is going to be the same thing as saying e to the integral to e to the negative x dx, like that, which is, e to the, exactly. So e to the integral of e to the negative x dx is just negative e to the negative x, like this. Looks kind of silly, honestly, but that is the integrating factor in this case. And so this is a good example to show you that sometimes these integrating factors look kind of weird, but in the end, they'll actually work out and it'll really help the problem along. So next step is to multiply this original ODE by the integrating factor. So just dy dx e to the negative x plus y over e to the x times e to the negative x equals 1 over e to the x times e to the negative x. Okay, so we've multiplied everything by the integrating factor. And so now we just need to undo the product rule here. And so this is always the case. So it'll be the derivative times the integrating factor, in this case e to the negative x, times the variable you're solving for. So here that's going to be y, because we're interested in y. So this will be equal to the same right side, so the right side didn't change at all. So this is e to the negative x times e to the negative x. And that's because I just rewrote 1 over e to the x as e to the negative x. So now we integrate both sides with respect to x. And so we should end up with the right side with no derivative, e to the negative x, y equals the integral of e to the negative x times e to the negative x dx. And so here's where I say the calculus 2 knowledge kind of comes in. because you've really done the ODE part already. Now you just need the knowledge to solve the integral. So in order to do that, in this case, it's going to be a u substitution. So I noticed that this here kind of looks like the e to the negative x. That's kind of an alarm bell for a u substitution if something kind of looks like something else in the integral. And so here we're going to say u equals e to the negative x. All right, so then du equals e to the negative x dx, because the negative from here came down and canceled with the negative that was already there. So we can say e to the negative x times y equals the integral of e to the u times e to the negative x times dx, but dx is actually du over e to the negative x. So here you can see why we set u to be negative e to the negative x. So these two cancel, and now you're left with just the integral of e to the u du, like that, which is, of course, e to the u plus c, which in this case is equal to e to the negative e, I'll write that a little bit better, e to the negative x plus c. So recall what the left side was. So e to the negative x equals e to the negative x. This is multiplied by y, sorry about that, plus c. So all that's left now is to divide both sides by this quantity right here. So then we have y equals 1, because these two are the same quantity. So when you divide the left side, or divide the left side from the right side, these two are going to cancel. So this is going to be 1 plus c over e to the negative x. And so this is an acceptable final answer, but we can kind of rewrite it. Just remember that 1 over e to anything equals e to the negative that something. So in this case, 1 over e to the negative x, we bring that to the numerator, and so 1 over e to the negative x will in turn equal e to the negative of negative e to the negative x. So this is just going to be e to the negative here cancels with the e, already negative, so e to the negative x. All right, so with that in mind, we can kind of make this look a little bit better. So we can just say y equals 1 plus c e to the negative x. And that's going to be our final answer for y using the technique that I showed. All right, so another example down the hatch there. And it's, even though it looks really kind of complicated, when are you ever going to see an e to the something? But even when the integrating factor looks like that, it still ends up working out nicely in the end. I thought this was a cool example to demonstrate how powerful this is, how it still works with really weird integrating factors. Okay, so I think we'll go ahead and do one more example here. All right, so for our final example, we're just going to do 1 ty prime minus y equals t squared e to the negative t, like that. All right, so first things first, divide by what's in front of the derivative, and I'm going to rewrite the derivative with respect to the variables in the question as well, using Leibniz, however you say his name, notation. And so this turns into dy dt minus 1 over t times y equals t e to the negative t. All right, Second step, always find the integrating factor, which is a variable or is a function of the variable that you're not solving for. So it equals e to the integral of the negative 1 over t dt, which equals e to the negative ln t. But remember, if it's a natural log, you can take out whatever in front of it and move it into the exponent of the natural log. Okay, so that means that this equals e to the ln to the t to the negative 1. And of course, e to the ln of something is just that something. So this is t to the negative 1, or if you want, you could say it's 1 over t. It's the same thing. So now we multiply everything by that integrating factor. Multiply this, multiply by 1 over t. So we have 1 over t times dy dt minus 1 over t squared y equals e to the negative t. Okay, so then we undo the product rule right here, which takes the form of a derivative with respect to the variable you're not solving for, times the integrating factor, in this case 1 over t, times the variable that you are solving for, in this case y, equals e to the negative t. So take the integral with respect to t of both sides, so this leaves you with 1 over t times y equals the integral of e to the negative t dt, like that. So we just find this integral over ty equals negative e to the negative t plus c, like that. And that integral is, throughout this series, I'm not going to be really explaining the integrals very much if they're gone over in depth in Calculus 2, but of course I'll work through them. So if there's integration by parts, for example, I will do the integration by parts, but I won't go over it as if I'm going to be teaching it. So we solve for y, and so we multiply everything by t. So this leaves us with y equals negative t e to the negative t plus tc. So that's going to be our final answer for y. All right, so those are just a few examples, and every single ODE of this form works this exact same way. So as long as you can do these examples yourself, then you should be totally fine, and you should definitely know the method. So thank you everybody for watching. Let me know if there's any other specific examples you want me to go over, and I'll be happy to do so. Thank you.